Hi everyone, I'm Ronald Chung, a Smart Nation Solutions Architect Lead from Amazon Web Services for ASEAN region. Today, I'm going to show some demonstrations to illustrate how AWS could help you to build your own data-driven smart city. In AWS, we have a smart city blueprint to ensure the data can get through the proper journey in order to help customers to achieve their ultimate outcomes. We have appropriate services and building blocks to handle the batch and real-time data ingestion, making sure the data can be stored in the data lake in the most appropriate format, and data processing pipeline to ensure the batch data as well as real-time data can be curated in a digestible format for subsequent consumption stages by analytics and AI ML. And finally, we have a broad spectrum of services to help delivering insights to end users so that they can achieve their final outcomes. And depending on different smart city use cases, different AWS services can be selected into these building blocks within this blueprint to realize a smart city. And today, we are going to demonstrate a number of use cases to you that leverage this blueprint for us to design the proper architecture. Let's have a look at the first use case example, the social media sentiment analysis. So on the left-hand side, we have the social media feeds, and these are real-time in nature. So that's why we are utilizing the real-time ingestion block processing technique to ingest data. And we are using the easy tool to run the social media feed crawler. And all these social media feeds will be feed forward to the Kinesis Firehose services here to buffer this real-time data. And at the same time, the data will be being stored into the S3 bucket in the most appropriate format. And this data stored in this S3 bucket is called the raw data. And once the data is being landed into this raw bucket, the Lambda functions will be triggered to do the data processing. And it will subsequently call the AWS Translate and AWS Comprehend to translate non-English tweet of media feed into English first, and then it will subsequently call the Comprehend to do the sentiment analysis. Once this analysis is being completed, then it will be utilizing the Kinesis data analytics to further massage the data a little bit before they are being stored into two separate buckets called the S3 entities as well as S3 sentiment. So the S3 entities consist of the tweet informations or related informations, and the sentiment bucket will be storing the sentiment related information of the social media feed. Once all this data is being landed into the S3 bucket within the data lake, then we can make use of AWS Glue for data cataloging, Athena for data scientists to do data discovery, and QuickSight to create dashboard to present the associated insights from this sentiment analysis. Let's have a look at this S3 console. So as you can see, we have the S3 bucket called the social media dashboard tweets bucket here. It consists of three subfolders, namely the raw, the entities, and the sentiment data. So using the Kinesis Firehose, let's have a look at the raw data bucket. You can see within this folder, it will be further organized into a hierarchy according to the date. So the 2020 here, 11, 15 will be the date, and then the hour, and then you can see that we have the data being gathered here. So these are the data being stored into the S3 bucket. They are being organized according to the year, month, date, hour. These are all automatically being formatted by the Kinesis Firehose. So next, let's have a look at the AWS Glue. So the AWS Glue can easily provide the data cataloging capability to form the table from the S3 data, from the data stored in the S3 bucket. So you can see that we have different locations here, the S3 locations from the sentiment, and this one is from the entities, and this one is from the raw bucket. So these are the three tables that are completely constructed directly from the S3 folder that you can see in the architecture. And once you have all this table in place, Data scientists can make use of Athena for data discovery. So you can see that here, these are some ad hoc SQL query that you can run based on this data, and you can actually see the results retrieved from the data directly stored from the S3 bucket. So you can see that once the data is being landed into data lake with S3 as the primary storage, subsequent processing becomes very easy, and you can directly access the data using traditional SQL query based on the Athena services. And finally, you can use QuickSight to realize the analysis results. So first, here is the data source. So on the left-hand side, you can see in the QuickSight, you can easily access the data from the S3 bucket, and you can use the Athena to prove the working status of your SQL statement first, and then you can employ the same SQL statement in QuickSight to end up with the data source appeared within this tile. So it consists of the geographical data, the country, entity, the language, all the things related to the Twitter feeds or the social media feed. So let's see how we can craft up the data. So let's say if I would like to create a new chart here, I can simply click the Add Visual, and you can see that there is a panel appeared here, and you can easily show here, I want a funnel chart, and this funnel chart could be grouped by the source, and the value here would be the number of different Twitter feed here. So you can see right away the top, that is the largest number of Twitter feed is originated from the Android mobile phone, and then the next highest number of tweets Twitter source will be actually from the iPhone here. So you can see that from the drag and drop operations, you can easily create new charts here. There are some other charts available for illustration purpose. You can count the distinct type of Twitter by proportion, okay? And you can count the number of Twitter feeds segregated by different sentiments category, mixed, negative, neutral, and positive. The rough proportion of the two of different sentiment segregations. So you can see that most of the Twitter feeds are neutral, some of them are negative, and some of them are positive, and with a handful number of mixed sentiment. But let's say I can drill it down and to exclude the neutral, and then you can see we have a mixed proportion being more visible here, negative being dominant, and the positive being the second largest proportion here. And we can also count the number of languages in terms of the feed number. Above 100K of the feeds are actually English language, and followed by some other language, the French, Dutch, etc. You can also utilize the geospatial plot. So you can actually see that, well, within the Singapore region, which part consists of the negative sentiment social media feed, which one is positive, which location is positive. And you can see basically around the world, because we are collecting the social media feeds all around the world here. So there are some geolocations in the other countries that are providing the social media feed as well. So that is the social media analysis demonstration. Now let's have a look at the other example use case, which is the air conditioner performance monitoring. So again, on the left-hand side, we have the data source. In this example, we also have the batch data ingestion. So the batch data is coming from the data.gov.sg, which is the open data portal in Singapore. And in particular, we are fetching only the weather information data here. And on the other hand, we have an IoT sensors the LoRa sensors here. So we have the LoRa gateway, we have an Arduino platform connecting to a sensors, monitoring the temperature and humidity in my living place. That means my home. So the sensor is somewhat like this. So this is the Arduino sensor platform with a dangling sensors here that sends the temperature as well as the humidity. So we have two kinds of data ingestion, the batch data ingestion as well as the real-time data ingestion here. And since we are dealing with the IoT devices, so in AWS we have the IoT core to receive the IoT sensors message through the MQTT protocol. And we can also leverage the IoT rule services to direct data to different data destinations. So in this case, we have the Lambda functions to modify the data a little bit and store it in the DynamoDB here. And then later on, we have another rule to send the data directly to Kinesis Firehose that stream the data to the S3 bucket as well. But we have a Lambda data here because the Lambda function here is to inject additional data into the raw sensor data. And in this particular example, the sensor data doesn't come with the timestamp. So the Lambda functions here is to serve as a pre-processing of the data so that we can inject the timestamp information before they are being stored in the S3 bucket. And on the other hand, for the data being fetched from data.gov.sg, that is from the Open Data Platform, we are using the EC2 instance to call the API to connect to this Open Data Platform to fetch the data. And this data will then be stored into the S3 bucket as well as in the document DB because the data is in the JSON format. And as we have mentioned earlier on, the data lake is not necessarily restricted to S3 as the data storage. And as a matter of fact, we need to find the most appropriate storage for different kind of data. And as we would like to preserve the raw data as much as possible, utilizing the document DB to store the original data from this Open Data Platform would be the most appropriate services to utilize. And we also have the batch data processing in the form of a Lambda function, which is a serverless architecture. So these Lambda functions will periodically reach out to the S3 bucket and process the data so that in the batch data can be processed in batch to the appropriate format for subsequent data consumption. And in this particular example, we process the data for forecasting purposes. And like in the previous example, we can utilize the AWS Glue, Athena, and QuickSight to create the dashboard easily. And in this case, we also have an EC2 to serve as a serving layer. Essentially, it just provides a web app portal to provide some real-time data information for the sensors as well as the observatory data. So let's have a look at the AWS IoT core here. So as I have said, this data is being, the sensor data will send the humidity as well as the temperature data through the MQTT protocol. So through this IoT console, I can simply subscribe to the sensor topic here, and then you can see that the data is actually being populated and sent to AWS IoT core in a real-time manner. So in this particular demo, the sensor will spit out the data every 4 or 5 seconds. And in terms of the web app, we can utilize the document DB, which store the Singapore weather informations. So we can actually plot the temperature as well as the humidity. And all this data are being fetched from the document DB and presented the information here in different locations. And at the same time, we can serve the real-time data of the sensor as well. So these are the sensor historical data from Sunday to, actually there are 24 hours of data here. And same for the humidity as well. You can see the 24 hours variation of the humidity level in my home, as well as the temperature variations. And the intention of this use case is to analyze the effectiveness of the air conditioner. That means disregarding the variations of the outside temperature, how effective is the air conditioner can maintain the temperature in my home environment. So to illustrate the real-timeness of the data, so here is the sensor. So now the humidity level is roughly 51%. If I press my thumb on the sensor itself, you can see that the humidity actually rise accordingly. So now it's rise to 60% and 66 now. So if I remove my thumb, then later on the humidity level will drop down. So probably due to my moisture, maybe I'm sweating a little bit for this demo session, so that's why the humidity increased when my thumb touched the sensor. So you can see that this is how the serving layers work, and we can visualize the real-time data from the sensor as well as the observatory weather information. And we also mentioned about the forecasting capability in AWS. So in here, you can see that we have the AWS Amazon forecast. And let's have a look at the sensor humidity forecast information here. So you can I have actually pre-trained a predictor. So based on the date here, and I can predict the humidity from 18 to 19, for instance. So the sensor number is 111, so I can get the forecast value. So you can see that these are the forecast value available based on the predictor trained from the historical data gathered from the sensor itself. So you can see that the humidity can be predicted according to P10, P50, and P19 forecast curve. And for Athena, you can see that we can, like the sentiment analysis demo, we can run the ad hoc SQL query here. So these are the data from the observatory as well as the sensor data. So they are from two separate tables. So for subsequent analysis purpose, we need to join these two tables together. So we can simply run this query, and you can see that we have the date, we have the humidity and temperature from the sensor. The location data is actually from the open data portal from Singapore Observatory. And these are the latitude and longitude of the observatory stations or the sensor locations. And finally, we can see the analysis part. So we are using the QuickSight to create the chart. So you can see the temperature variations from the Singapore Observatory and also the variations of humidity level. And well, it seems that my air conditioning works quite well because despite there is variation of external temperature, my air conditioner still be able to maintain a relatively stable temperature. And we can actually plot the number of readings in terms of varying temperature level, 26, 27 in different color. So you can see that the 26 temperature is here, but the number of readings is relatively small. And for the orange here, that corresponds to the temperature 27 degrees Celsius. It composed of the majority number here. So that means that my air conditioner most of the time obey my temperature settings, which is set at 27 degrees Celsius. But there are some up and down from time to time, but most of the time it is 27 degrees. So that means my air conditioner is performing quite well. And there are some other interesting insights here. Whenever there is a peak at the temperature here, there is a trough or the lowest value in terms of the humidity. So another data point here, this is the peak of the temperature, and this one will be the lowest point of the humidity. So that means there is an inverse relationship, seems to be an inverse relationship. So we can utilize a scatter plot with the horizontal axis being the temperature and the vertical axis being the humidity level. So we can have this line being plotted. So it confirms our belief that it seems to have a inverse relationship between the temperature and humidity level. So even not an observatory or a weather expert can still find some useful insights from the data. So that is the air conditioner performance monitoring use case. But if you look at this architecture diagram and compare it with the previous one, you can see that these two architectures are substantially different. And why is that? Because we don't believe that we have a one-size-fits-all kind of solution architecture for different kind of use cases. But we can have a unified blueprint for our customers to architect different kind of solutions. And in this case, the customer can, well, enjoy the benefit of, first of all, the flexibility in architecting the solutions. And second of all, you can utilize the minimum number of services in order to architect your solutions, leading to cost savings. You can start small with your smart city solutions with a handful number of services, but then when you need to scale up or add new data use cases, you can slowly add more services on top of it, and at the end of the day, you end up with your own set of solutions. So that's the mentality of the smart city blueprint in AWS. Let's get to the final example. So in this case, we are also utilizing the data.gov.sg, the open data in Singapore. And we are trying to fetch the camera data deployed within the city, and in particular, the transportation snapshots. So we get all these snapshots and trying to utilize AWS Recognition services to determine the number of vehicles within that snapshot, and in the way that we can estimate the traffic density within the city at different point of instance. So again, the data flow from the left all the way to the right. So we use EC2 and to make use of the API call to fetch the snapshots from the open data platform. And all of them will be stored right away into the S3 bucket. And subsequently, it will trigger the Lambda, the serverless functions, to call the recognition services to count the number of vehicles here. And this number of vehicles will be further stored in the DynamoDB, so as a piece of information. And after that, the Lambda functions will fetch also the data from the DynamoDB for the historical vehicle count and process it in the way in batch and store the traffic density data back to the S3 bucket. And after that, everything follows the same path. We have the AWS Glue, Athena, and QuickSight to provide the dashboard for insights presentation. So to have a look at the actual recognition operations, so let's have a look here. So this is the AWS Recognition. So what you need to do is to drag the image snapshot here, and then it will analyze it and return you with the vehicle detected or some other objects detected within this snapshot. So in this particular example, we can detect the person here as well. They are probably the road worker standing alongside on the sidewalk of the road. And these are the detected vehicle. And the detected results will be in the form of the JSON format. So we have the bounding box informations, we have the type of the objects being detected, the confidence level, etc., etc. But in this particular example, we are interested in the number of vehicles only. So this is a relatively simple demonstration. So we can just jump right away to the traffic analysis. So based on this, we can have the geospatial plot based on the location of the snapshots being acquired. and use the size to indicate the level of traffic density. And the bigger the bubble here, the higher will be the traffic density. So you can see that in Singapore, the central regions, they consist of higher traffic density, which is quite reasonable. And for more remote region, we have smaller bubble around here. And you can also plot the proportion of traffic for different point of capture in the form of a pie chart. And you can also plot the average vehicle count by date here. So you can see there is up and down for sure, because at daytime there could be more traffic, especially in the morning. Here we have the first peak when people need to go to work or go to school. Okay, and at night around 7 p.m. there is another peak. So this pattern repeats day after day. All right. And there are some days that could be lower in terms of traffic. So that could be holidays, that could be the weekend, and that could be some other reasons. But it also reveals the potential of data correlation, because you can see the data up and down. But if you have some other information in place, let's say if you have another database consisting information related to what, like construction work in a particular junction. So in that case, you can correlate the high traffic count or the low traffic count to see if it is correlated with the construction work in a particular location. Then from that point onwards, you can refine your strategy whether certain construction work in place would affect the potential traffic density at different city points. So that could be one extended use case on that. And all you need to do is to bring additional dimension of data into the data lake itself. And one other thing I would like to draw your attention here is that, well, apart from the solid line here, there is also some other transparent line appeared here, or the shaded area here. They are actually referred to the forecast. So within QuickSight, we also leverage machine learning technologies to do forecasting as well. So you can see that we can, within the QuickSight, we can project the future traffic pattern as well. And so that the corresponding stakeholders can have a glimpse of what the future is going to look like. And some other plot here by the bar chart for different locations at different dates, etc., etc. So in all, these are the 3 use cases or 3 example architecture that I would like to go through with you through this session. And again, one important point is that we have one unified blueprint to design smart city solutions, but the number of possibilities will be unlimited, because you can basically architect a wide range of use cases based on this blueprint architecture. So thank you for staying with me for this sharing sessions. There are actually a lot more AWS Rapid solutions available. Please check out the QR code here or visit the URL here for more information of AWS solutions available for your considerations. Thank you.